Good day, everybody. We're going to continue conference hours and the series that we're doing, how to dissect equations, by going over Pascal's law. Um, Pascal's law is something that we just went over very recently, and we are going to be doing a lab, with hydrostatic um, concepts here. So I thought that Pascal's law would be best. So we're going to go through this. And, when we dissect an equation, the first thing that we want to do is we want to ask, what is Pascal's law? So, uh, you know, one way that we can think about this is the principle of transmission of fluid pressure. I don't know if that's a really good way to remember it, but if we look at it on Wikipedia, we can get a pretty good definition. And it says that a change in pressure at any point in an enclosed, incompressible fluid at rest is transmitted equally and undiminished to all points in all directions throughout the fluid. And the force due to the pressure acts at right angles to the enclosed wall. All right, so notice here that I made these bold. These are important. So I did that for a reason. They're special. And if we change these things, then Pascal's law doesn't necessarily work. So first question you might want to ask yourself is, what is an incompressible fluid? Well, an incompressible fluid is one that can't be compressed. That means that when we squeeze it, the fluid would rather change volume or change its shape so it'd rather change its shape than be compressed. So one way that you could think of this is, or let's think of this. The first example that people think of would be an example of an incompressible fluid is water. Uh, if you think about one of those stress balls, squeezable stress ball filled with water. If you think about these little balls here that you see in the stores that you can squeeze, and especially this right here, uh, you can see that these balls that they squish, instead of compressing to be a smaller ball, um, they expand. So just so that way you can have you see here, this is the original shape of the ball. And when we squeeze it, instead of the ball getting smaller and remaining the same size, it would rather change shape. So this means that this is filled with an incompressible fluid. My challenge to you is to try to think of another, what is another incompressible fluid? People immediately go to hydraulics whenever you think of this concept. So the first thing that I would think of is oil, motor oil specifically. Okay. So that's great. We now know what Pascal's law is, and we, might not have known what an incompressible fluid is, but now we kind of have a better idea of that. So the other point that we need to make is that the fluid is at rest. So what does it mean for a fluid to be at rest? In fact, let me make this a little bit. Give me just a second. So what does it mean for a fluid to be at rest? Well, for something to be at rest, anything to be at rest, the sum of forces acting on it, on an object, must cancel. So that would mean that if we have a fluid in some container, and there are no forces acting on it, then we have a fluid that is at rest. So you might think to yourself, well, Pascal's law says that if I were to press on this fluid, that it's going to, make sure that the pressure stays consistent and, things might change. This is correct. However, the motion doesn't come from the fluid itself. It comes from the action of you or whatever pressing on the fluid and uh, the force being transmitted that way. So let's now go into um, the next question, which is, what is the equation for this law? The equation for this law is is what you see here. And so, just like we do in the other videos, we're going to dissect this. So what is this delta P? Delta P is the change in pressure when some force is applied to the fluid. Rho is the density of the fluid. G is, of course, the gravitational constant at the surface. And delta H is the change in height from the pressure being applied. All right. So we have dissected this equation. Now let me try to illustrate this with, in your head by using some examples. Uh, for instance, when you sit in a bathtub, when you get in the tub, the the water doesn't compress underneath you. It changes shape. This is because water is an incompressible fluid. Another example, in fact, this has a little story with it. Um, the first time we ever visited Tennessee, we were staying at a cabin, and there was a jacuzzi or a hot tub there, and um, there was a hose that was inside the jacuzzi, and my son partially threw the hose out of the jacuzzi, and there was still water in there with one hose end of the hose in the water, and then another end down on the ground. I would say maybe 7 or 8 feet below the tub. And we left and came back, and the tub was empty. And that's because there was a difference in the pressure between where where the hose was in the tub and where the hose was on the ground. And the pressure at that difference at that point pushed all the water out into the ground around the cabin. So, you know, uh, you can find Pascal's law in many places. So this example is if you wanted, you could use this actually to do anything if you're trying to empty a pool or any concept like that. It's not just a hose type thing. Once you get a flow started, it's going to keep going until there's nothing left. So consider a tub or pool of water, some height, delta H above the ground. Let there be a hose inside. Let there be one end of the hose inside the tub, and then another outside of the tub, where H equals 0. Due to Pascal's law, the pool is going to drain. The pool or tub is going to drain. All right, so just to recap, we're dissecting Pascal's law. We said that it was a change in pressure at any point in an enclosed incompressible fluid at rest, and that pressure is transmitted equally and undiminished to all points in all directions throughout the fluid, and the force due to the pressure acts at right angles to the enclosed wall. I guess one last thing that I didn't touch that I would like to touch is this word undiminished. So if we want to be real technical, we can add in what is undiminished. How do we define this? Well, undiminished means that there are no frictional forces to dissipate energy away. So we find that all of the energy that is exerted into applying the pressure changes the shape of the pressure, or changes the shape of the fluid to distribute the pressure properly. All right, so I hope this helps. If you have any questions, please let me know, and good luck to y'all.